Lesson 7. Motion and Dynamics. Contents. The topics covered in this lesson are: review of basic physics concepts, basic physics quantities, scalars and vectors, basic kinematics, displacement, velocity, and acceleration, basic dynamics, force and torque, work, power, energy, mechanical advantage, gear and transmission. The tasks or activities for this lesson include: gearbox assembly task, basic physics quantities, scalars and vectors. Scalars are physical quantities with only magnitudes, such as mass, time, etc. While vectors are physical quantities that have both magnitude and direction, like acceleration, force, etc. Scalars are represented by a number that is, magnitude and unit, whereas vectors are represented by a number, and direction using a unit cap or arrow at the top and unit. Displacement. It is a vector quantity. The difference between an object's final position and its starting position. In other words, it is the shortest distance between the 2 points in space. What is the displacement when an athlete makes a complete round on the track shown? When an athlete makes a complete round on the track, the displacement is 0, since the initial and final positions are the same. Linear versus rotational motion. When a body moves from one point to another point in a straight line, it is considered linear motion. When a body moves in a curved path along the axis, it is said to be in a rotational motion. Average speed. It is the total linear distance traveled by the body to the time taken to cover that distance. Average angular speed. It is the total angular distance traveled by the body to the time taken to cover that distance. Acceleration. It is the rate of change in velocity. Average acceleration is defined as the change in linear velocity for that interval of time. Average angular acceleration is defined as the change in angular velocity for that interval of time. Here, the distance traveled is from xi to xf, that is, x1 plus x2, along the arrows mentioned. While the hypotenuse of the triangle is displacement, as it is the shortest distance. Linear versus rotational motion. Based on the explanation provided in the previous slide, calculate the average linear and angular speeds. To cover a distance of 400 meters in 20 seconds, its average speed is 20 meters per second. Linear versus rotational motion. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in its direction, and inversely proportional to the mass of the object. Torque tends to produce rotation motion. Torque is analogous to force in rotation motion, which causes a change in angular acceleration, and similarly, inertia is analogous to the mass in linear acceleration terms. Work. Work is equal to the product of applied force and the amount of displacement along the line of action of that force. If the net force is perpendicular to the motion, then no work is done. If you push on an object and it doesn't move, then no work is done. For instance, if you hit a wall hard, the force applied to the wall will not work. This is because the wall displacement is 0 in this case. In the case of spring, work done is the product of the force applied and displacement caused in the spring. Energy. In physics, the law of conservation of energy states that the total energy of an isolated system remains constant. It is said to be conserved over time. This law means that energy can neither be created nor destroyed. Rather, it can only be transformed from one form to another. In this image, we can observe that potential energy is getting converted to kinetic energy, as the trolley slides down. Work-energy relationship. With the principle of the law of conservation of energy, the work done by a net force acting on an object causes a change in the mechanical energy of the object. Power. It is the measure of the amount of energy transferred per unit of time. It is the product of force on an object and its velocity. Power is a scalar quantity, and its SI unit is watt. What is mechanical advantage? In a lossless system, the power transferred from input to output is equal. Here the weight of the object F1 is 100 pounds, F2 is 50 pounds, therefore MA equals 2. With mechanical advantage, we can measure the force amplification of the tool. The tool in this case is a pulley system. This method is used in designing systems such as levers, pulleys, wedges, etc. Activity 1. What is the mechanical advantage of this pulley system, if the weight of an object is W? F1 is the force produced by a machine. F2 is the force applied to the object. Activity 1 solution. The mechanical advantage of this pulley system for weight, W, is 4. This implies that by using 4 pulleys, the input can be 25% less than the weight of the object as the input force gets magnified 4 times. Gear and transmission. Gears are popular power transmission tools that find applications in fields that require amplification of the energy from watches to heavy machinery. With the use of gears, power can be transmitted in different axis planes. Gears' teeth mesh and transfer power from one part to another. Purpose of gears. Gears are generally used for one of 4 different reasons: to reverse the direction of rotation, to increase or decrease the speed of rotation, to move a rotational motion to a different axis, to keep the rotation of 2 axes synchronized. Need for gears. The use of gear settings depends on the application of scenarios. In this picture, while the cyclist goes downhill, with the help of gravity, the load on the cyclist is low. As a result, we can use gear settings with low torque requirements. It's vice versa in the case of uphill. Need for gears. The use of gear settings depends on the application of scenarios. In this picture, while the cyclist goes downhill, with the help of gravity, the load on the cyclist is low. As a result, we can use gear settings with low torque requirements. It's vice versa in the case of uphill. Spur gears. They are the most widely used gear types. They transmit power in the same plane. When 2 gears are meshing, the gear connected to the power source is a driver and the other meshing gear is a driven gear, which usually rotates in opposite direction as that of the driver gear. Here, gear A is a driver gear, and gear B is a driven gear. Gear systems. The use of multiple gears constitutes a gear train system. They are used for high-power multiplication or division. In this example, suppose a motor turns gear A in an anti-clockwise direction. Which direction does gear B turn? Which direction does gear C turn? Does gear C revolve faster or slower than gear A? Gear systems. Gear B turns in a clockwise direction. Gear C turns in a counterclockwise direction. Gear C revolves slower than gear A, due to the large size of gear C. Gear systems. As the name says, idler gear doesn't change the speed or torque of the driver and driven gear. Idler gears are generally used when the direction of rotation of the driven gear is to be the same as that of the driver gear. In the previous example of 3 gears, the middle gear changed both direction and gear ratio, hence do not qualify as an idler gear. Gear ratio is also called speed ratio. It is a quantitative measure to calculate the parameters of gear while designing a gear system. It is the ratio of the number of teeth of the driven gear to the number of teeth of the driver gear. In this image, the driver gear A has 60 teeth while the driven gear B has 30 teeth. As a result, the gear ratio is 2. This implies that driven gear B makes 2 rotations for every 1 rotation of driving gear A. Examples of gear ratio. In this slide, the gear ratio is 3, which means that the driven gear B makes 1 rotation for every 3 rotations of driving gear A. Working out rotations per minute. In no-slip conditions, since the linear distance traveled by each gear is the same, the arc length of gear A is equal to the arc length of gear B. Therefore, radius into theta of gear A equals radius into theta of gear B. Theta of gear A divided by theta of gear B equals radius of gear B divided by the radius of gear A, also equals the number of teeth of gear B divided by the number of teeth of gear A, for gears of the same pitch. Therefore, omega A into NA equals omega B into NB. Here, gear B rotates at a speed of 240 revolutions per minute. Activity 2. Calculate the angular velocity of gear B. Activity 2 solution. The angular velocity of gear B is 20 revolutions per minute. Gear ratios. To calculate gear ratios of a gear train of 3 gears, first works on gears A and B and then on gears B and C. For the system shown, gear A revolves at 60 revolutions per minute in a clockwise direction. What is the output in revolutions per minute of gear C? In what direction does gear C revolve? Gear ratios. First, consider gears A and B and then calculate for omega B. Now, consider gears B and C and then calculate for omega C. Gear C rotates at 120 revolutions per minute in a clockwise direction. Compound gear ratios. The compound gear consists of two or more gears of different sizes fixed together on the same shaft to rotate at the same speed. The application of compound gears is when we require a high gear ratio in a small size. The compound gear train can give higher speed reduction with less center distance between input and output shafts. To calculate the gear parameters, follow these steps. Split the compound gear into two parts. First, treat gear A and gear B. Next, treat gear C and gear D. For the compound gear system shown, what is the output in revolutions per minute of gear D? What is the direction of rotation of gear D, if gear A rotates in a clockwise direction at 30 revolutions per minute? Compound gear ratios. By following the steps, for gears A and B, the speed of gear B is 90 revolutions per minute. Since gears B and C are on the same shaft, the speed of gear C is also 90 revolutions per minute. Next, considering gears C and D, the speed off gear D is 360 revolutions per minute. Gear D rotates in a clockwise direction. How differential works. Watch this video to understand the working of a differential more clearly.
Formations like these require long hours of intensive drilling and careful judgment. When the troop goes around the corner, the riders on the outside of the turn have to adjust their speed to keep even with the riders on the inside. The man on the outside has to ride a lot farther and a lot faster in order to keep up with the parade. The outside wheels must spin faster than the wheels on the inside, because they have a greater distance to travel in the same length of time. When a wagon turns a corner, the wheels can travel at different speeds because each one can turn freely on the axles. And in the early automobiles, the rear wheels turned separately and only one wheel was connected to the engine. But when only one wheel was driven by the engine, it had to do all the work, and it couldn't get a good enough grip on the road to do its job properly. So the one-wheel drive was soon out of date. But if two wheels are locked on an axle so that they are not free to turn separately, one or the other has to slide. So engineers had to find a way to connect both rear wheels to the engine without sliding and slipping on turns. The device which makes this possible is a part of the rear axle. It is called the differential because it can drive the rear wheels at different speeds. The differential looks complicated, but once we understand its principle, it is amazingly simple. These two wheels are mounted on separate axles and supported by a frame. so that they can revolve freely at different speeds. Let's fasten a spoke on the inner end of each axle so that by turning the spokes, we can turn each wheel separately. With a bar or crosspiece, we can turn both wheels in the same direction at the same rate of speed. Let's get something to hold this bar in place so that it will press against the spokes. Notice that this support is not locked to the axle. It turns freely. Now we can spin the wheels by rotating the support. This is fine as long as both wheels are able to turn at the same speed. But let's see what happens when we go around the corner. With this arrangement, we cannot drive one wheel faster than the other. And if we stop one wheel, the other wheel won't budge. Let's put this bar on a pivot so that it can swing in either direction. Now, the bar can still turn both wheels at the same speed. And because it pivots, it lets one wheel turn even when the other is stopped. But if turned too far, the bar will swing around until it won't drive the spokes that turn either wheel. We need another crossbar and more spokes to carry on the job. When we stop one wheel, the crossbars will continue to push the spokes of the free wheel around. As long as both wheels are free to turn, the bars do not swing on their pivot, and the wheels move at the same speed. Now we have the working principles of a differential. To adapt the model for use in an automobile, we will have to make a few changes. In order to reduce the jerky action caused by wide spaces between the spokes, we will put in more spokes. Further filling in the spaces between the spokes gives steadier, more continuous action, and changing the shape gives firm, constant contact. Now we can make the gears thicker and stronger, and we have differential gears. The edges are cut so that they will fit together more smoothly and silently, and another gear is added to share the work of driving the axles. The principle is the same. In order to turn the support and drive the wheels, we can fasten a large gear here, connected by a smaller gear to a source of power. Notice that the power is connected to the differential at the center line. We can make our model more compact by moving the gears closer together. When we put our differential in an automobile, we have to leave room for the drive shaft, which carries the power from the engine. We may build the floor of the car above the drive shaft. But if we do, we won't have much room inside unless we make the top of the car high too. Of course, we could lower the floor and ceiling, but the drive shaft would be higher than the floor. This would have disadvantages. A shaft in the middle of the floor of an automobile would be inconvenient for passengers and would be awkward for carrying luggage. Today, engineers have found a way to make the car roomier and closer to the road without a clumsy shaft above the floor. The drive shaft from the engine to the differential is lowered out of the way, and the drive shaft is connected to the rear axle at the bottom. The new low center drive makes the rear axle quieter, stronger, and more durable because it gives better, smoother contact between the gears. The automobile of today with the low center drive is stronger and more rugged. Every part of the rear axle has been built to withstand strains far greater than it will ever meet on the straightaway or around the corner.
Activity 3. Making a gearbox. Taking readings and comparing the result with the empirical formula. Changing internal gearing and finding a new speed. Refer to the worksheet document attached for more details. Thank you.